Hello and welcome. In these notes, we're going to be taking a look at several parts of motion. We're going to break this down into short videos that reflect different aspects of motion, everything from breaking down vectors, what are vectors, to how to represent them in a picture, to how to calculate things with vectors, to defining vectors versus other quantities called scalars, and learning how to essentially define them in terms of physical quantities like distance and displacement, speed and velocity, and then later on acceleration. Remember to pause or rewind the video as you need to. Let's begin. Let's start off with basically this question with a very simple, seems to be a simple question. What is 2 plus 2? Well, of course we know it's 4, but the question is it always? Well, let's do an example to kind of see how this really sort of works. When a student walks 2 miles north, then walks 2 miles east, what is the distance they walked? Well, the distance, remember, is a path length. And length can never be negative. So that one is just as simple as distance is equal to 2 miles. Miles, MI is the abbreviation for miles, plus 2 miles, which is 4 miles. Right? That's the distance. Now, the displacement, on the other hand, right, is the change in position from starting point to finish line. And remember your directions. North typically goes up on a map, south goes down, east goes to the right, and west goes to the left. So according to this, we walk 2 miles north, like this, but then walked 2 miles east. That would be like this. The displacement, ladies and gentlemen, would be a straight line from start to finish, like that. What would be this displacement? Well, you can see it's a right angle, a right triangle there, and we need a little Pythagorean theorem to sort of figure that out. So we call this side A and this side B, and then we'd be looking for side C. So A squared plus B squared equals C squared, or we could reason this out that this is a 45, 45, 90 triangle. And in a 45, 45, 90 triangle, we have a special relationship of 1, 1, square root of 2, or I guess you could think about it as A, where A represents any number, kind of like 2. And this would be A times the square root of 2. So that means C would be 2 times the square root of 2. However, you can still break it down using Pythagorean theorem. Let's try. If we use Pythagorean theorem, we'd have essentially 2 squared plus 2 squared equals C squared, which is 4 plus 4 equals C squared, which is 8 equals C squared. Now, you know that if you have to take the square root to figure out what C is, well, C is the square root of 8. Now, the square root of 8 might be a harder number to come up with. The square root of 9 is 3. So the square root of 8, we're looking at about 2.9, roughly. So almost 3. But it's clearly, the point we're trying to make is it's clearly not the same as 4 miles. 2 plus 2 is not always 4. When we're talking about vector quantities, sometimes the directions will make a difference. in terms of how two vectors add up, especially if they're not moving in a straight line. Clearly, the direction changed and was not going in a straight line. So for this example, you were asked to define distance, which is a scalar, distance is a scalar, and displacement, which is a vector. Okay, so what are these things? Well, scalars are quantities that have magnitude only. The word magnitude means size. They're normal numbers and you can just add them, like we did here. Distance was simply 2 plus 2 or 4 miles. Vectors, on the other hand, have both magnitude, but they also have direction as well. You can't simply just add them. You have to take the directions into account. So vectors are represented as arrows, and the length of the arrow, the length of the vector is representative of its magnitude. So if something has let's say a fast velocity or a large force, those are examples of vectors, then you would draw them with long arrows. So some examples of vectors would be displacement, velocity, acceleration, force, momentum. Top off probably the 5 most common ones you're going to be looking at this year. Examples of scalars. Again, scalars are those quantities that just have an amount to them. They don't have a direction. So time, distance, mass, energy, speed. Those are all examples of quantities we're going to be working with that don't have any direction associated with them. You can't put time in a direction. You can't measure energy going to the left or up. And speed, when you talk about speed going in a particular direction, we have a name for that. It's called velocity. So let's take a look finally at what are called vector components. So components are going to equal essentially the kind of the legs of a triangle, kind of the way you could think about it. The components of the vector need to add up to form the vector. So for instance, for vector v below, draw the set of components. So here's what I mean by components. You have a vector that's represented by this arrow z, and it's pointing up and to the right. So if it's pointing up and to the right, you have part of the vector that's pointing to the right. Let's draw a blue dashed arrow going to the right, and I'm going to draw a gray dashed arrow going up. So this would be z vector, whatever vector z is. It could represent anything in the x direction, and then you've got vector z in the y direction. So I use a little subscript x and y to denote that. Okay. How many sets of components are there for any vector? Always 2. Always 2 sets of vectors. You will always have horizontal, in other words 2. There will always be horizontal and vertical components. Remember, components just mean the part of the vector that's pointing either in the x or y direction. That's all that means. So, you have horizontal x and y components of vector A. And this is where we're going to tie in trigonometry into this. If vector A is pointing up and to the right, then we have a component going to the right and another component going up. And again, I'm going to color code this. Blue going to the right and gray going up. Well, ladies and gentlemen, the blue side is the opposite side of the triangle. Not opposite. It's the adjacent side of the triangle. The gray side is the opposite side of the triangle. Adjacent always goes with the cosine of the function. Opposite always goes with the sine of the angle. Okay, so adjacent goes with cosine of the angle theta, and opposite goes with sine of the angle theta. 100% of the time, this is true. So now if you put this together, the actual component that's here is going to be A, the magnitude of the vector, how long, what this value is, times the cosine of the angle. So A in the x direction is equal to A times the cosine of the angle. A in the y direction, this gray component going upward like that, is going to be the vector magnitude times the sine of the angle. Let's take a look at a few examples. Remember, to find the horizontal component, it's going to be the vector magnitude A times the cosine of the angle. To find the vertical component, it's going to be the vector magnitude of A times the sine of the angle. Okay, let's take a look at a few examples. In the first one here, we've got the vector magnitude is 60 units, whatever that is, and it's pointing off in that direction. That's 30 degrees above the horizontal. So this is going to be our horizontal component, and the gray one is going to be our vertical component. The gray one is going to be A sub y, which is equal to A times the sine of theta. A is 60, so this is 60 sine 30. Plug that in our calculator. 60 sine 30 is 1/2 of 60, which is 30. Now for the blue component, the horizontal one, this is A in the x direction. This would be A times the cosine of 30 degrees. So it's going to be 60 cosine of 30. Plug that in your calculator. Remember, those of you with backwards calculators, remember to go 30, take the cosine, then times 60. So 60 cosine 30 is roughly about 51.96. So it's around 52. Okay, so in this next example, vector B is 60 units pointing 30 degrees above the horizontal this way. Well, it's really going to end up being the same thing, because you've got 30 degrees pointing this way, and you've got that pointing up. So you're still going to end up with 60 sine 30, or 30 going up, and you're still going to end up with 60, oops, wrong color. We're still going to end up with 60 cosine 30, because this is the adjacent side of the triangle, which is still 52. So that didn't change. But then what if we have a vector that's going straight down? Well, it has no angle. Therefore, we have C in the x direction is 0. You don't have any vector components in the x direction because it's only going vertical. C in the y direction, however, would equal negative 40, negative because we're going downward, and 40 because that would be the actual direction. Now, how do we come up with negative 40? There's another way we can kind of reason it out, and it would be this. Theta, if we looked at the actual angle, could be taken from 0 degrees here, and the entire angle there is 270 degrees. Well, you could look at it as in the x direction, it's going to be 40 times the cosine of 270. And if you go 40 cosine 270, because 270 is 270 degrees, is the whole angle measurement from all the way over to the right to all the way straight down, and you end up with 0. But if we go 40 sine of 270, well, the sine of 270 is negative 1, and negative 1 times 40, that's where we get the negative 40 from. So, but you can reason it out to say that we've got a vector that's only pointing in the y direction, and it's pointing downward, hence the negative.